one is not a line.
Yes, that's why we say it's not exactly.
So I read level 1 and then update, and then come back to the loop again. Then why this one after? So why this one rest and
clock is always coming. This is a clock.
What's the difference between these two states? Are there any difference?
No. It's just a clock. A clock is a continuous pulse at a particular frequency. Just like when you say your processor is running at a particular frequency, correct? That frequency is what? It's a clock frequency.
So at this state, this one will not work.
I mean, we are not saying that anything is going to work or not going to work at that edge. It's just that within the clock cycle, everything will happen.
Which one is considered as a clock?
The whole thing, from one edge to another edge. Okay, today I am going to do a recap of yesterday in a summarized way so that you sort of understand what we did. So yesterday we actually covered the first 4 stages of your processor, which we haven't finished it. The last cycle has not been completed, which is the write back stage. Okay, so I'm just going to do a quick recap, okay, of how the whole thing is flowing. Okay, so this is important. If you do not understand this chapter, then the next chapter will also be an issue. Correct? And then the last few chapters of the semester will also be an issue because we're going to come back to this again. Okay, we're going to come back and improve the processor. Okay, so this chapter and the next chapter is very, very important, okay, to understand how the whole processor decodes the instruction step by step and gets it to perform the desired operation. Okay, so the first stage, as we saw, is the fetch stage, which basically means you are fetching an instruction from memory. Okay, and your instruction memory is just a memory which stores all your program instructions. Okay, so you can think of it as a continuous flow, and each line is one address. And when I specify an address, that instruction in that address will be fetched from the memory and sent to my decode stage, which is to my processor. Your program counter is nothing more than a register that holds the address of where I'm supposed to fetch this instruction from. And by default, you have a add with 4. Okay, so that's why we say that the moment my processor is executing this current instruction, I will automatically point to the next instruction to be executed because this is hardware triggered. Okay, so memory is nothing more than sequential circuit, okay, which is storing all your instructions or your data. And when I specify and put an address, what I get is the content at the address. Okay, so memory is nothing more than just a storage. Okay, if I store instructions at this address, then when I supply an address, I get the instruction. Okay, if I'm storing data, then when I supply an address, I get the data. Okay, so it's just a place to store information. So if I say that this is instruction memory, in each address, I'm storing an instruction. Okay, so example like this. Okay, so in each address, I store an instruction which is 32 bits long. And that is how you view instruction memory. Your adder is a hardware adder, okay, and we say it is a combinational logic. When we say something is combinational, means it is not triggered by any clock. That means as long as there is some data here okay, if I provide some data here, FF, blah, blah, blah. Okay, as long as I present some data to the hardware, it will perform the operation and give me the output. There is no clock trigger, there is no code executor, nothing. It is just a hardware block. Okay, input is provided, the hardware will trigger, and I will get the output. So in this case, it's nothing more than adding two 32-bit numbers. In all our systems, we talk about clocks as the key to running a system. Okay, why? Because everything is based on a clock, especially when you're talking about a processor. Okay, so when you say this processor is running on a 20 megahertz clock, it's running on a 1 gigahertz clock or whatever. So that is the overall system clock. That's the overall system clock. And that tells us how fast your processor is executing. Okay? But of course, if you talk about a complex system, you may have different clocks for different subsystems. Okay, so even though you say your main processor is maybe running at 1 gigahertz, okay, that is only your main processor. But you may have a lot of other subsystems or subprocessors that may run at other speeds. Okay, so it's not that the whole board, everything is running at the same speed. Now, we say that the PC is read and is automatically updated to PC plus 4 as the next rising edge. So what happens here? Okay, so if I assume that right now PC is 104, okay, that means what is presented to the instruction memory is address 104. Then by default, this 104 is already added to 4, and what is standby here is 108. Okay, when we say that the clock come in, okay, this clock is going to trigger both your program counter as well as your instruction memory. So what is going to happen? When your instruction memory gets triggered by the clock, the data at address 104 is going to be presented out. Okay, and at the same time, okay, 108 will come in here. Okay, so from 104 it will become 108. And when 108 comes in here, the hardware will again add 4 and bring it to the next address, which is 112. Okay, so each time you present an address to the memory, when the clock comes in, the instruction at that address will get clocked out. Okay, and then your hardware will trigger and prepare the next address for you by default, which is PC plus 4. Okay, so that is why here we say that it is not exactly at the same time. It looks like it's the same time, but it's not exactly at the same time. Why? Because there is a time difference for your adder to complete, correct? Okay, so even though the add block is there, the PC is there, everything is there, but when the clock comes in, the current PC is sent to the instruction memory, and by the time the next PC plus 4 come back, the clock already passed, correct? So it will not update until the next clock come in. So that is why we say it's a clock system. Now after we get this, we do the decode. Okay, so this is what we saw yesterday. And in decode stage, the first thing we need to know is the register file. The register file is nothing more than a memory that is within the processor. Okay, it's within the processor. Only thing is very small memory. Why is it very small? Because you only have 32 bits per register and total of 32 registers. So it's very small memory that you have to store your information to make your processing very fast. That is how your RISC processor works. In RISC system, you try to keep everything within the register and do operations on the register. Okay, instead of, for example, a CISC where you can directly manipulate from the memory. Okay, so the register file, you have 3 registers you can specify, which are your 2 read register and 1 write register. And when you have a write register, you have write data to specify as well. Okay, and then there is a control signal here. And this control signal tells us whether we are going to update any particular register in this instruction. Okay, so some instruction you need to update, some instruction there is no need to update. So in this example here that we saw, when I say add 8, 9, 10, you know that your 9 is your RS, RT, and your RD here. Okay, so this is your 9, 9, 10, and 8. Okay, RS, RT, and RD. So when I present RS, RT, and RD here, whatever is in register 9. So inside here there is one register which is register 9 and another register which is register 10. Correct? So whatever is the content inside here will come out here, and whatever is the content here in register 10 will come out here. Correct? That is what a register file is supposed to do. So the register file is again like a memory. Correct? Why? Because how does memory work? I give you the address, you give me the data. Correct? Only thing, the concept is here you have multiple address bus. Correct? So one address bus gives me one data, another address bus gives me another data. That is the same concept as memory. And the result to be stored, so in the bits 15 to 11 is the write register. That means which register I supposed to write to after I finish this particular operation. Okay, and the last one is a write data. So this write data is only available after I complete this instruction. Correct? That means I must pass through the ALU stage, pass through the final write back stage, then the answer is that. In a add immediate instruction, what do you see? You see that you have your RS and you have your RT and you have your immediate value here. Okay, so this is your 22, 21 and your negative 50 here. So the challenge we saw is if I try to do the same mapping, what happened? Okay, your register 21 is in the sort of wrong position, right? Because your register 21 in this case is the place where I want to write to. Okay, so if I try to follow the same mapping, it doesn't work because it is now currently pointing to a read register, and I want this bits 20 to 16, which specify my RT, in this case to point to my write register. Okay, so that is the thing. Okay, so how do I overcome this challenge? I introduce a multiplexer. Okay, so a multiplexer is just a simple hardware that channels the appropriate data to the output pin. Okay, so I can have multiple input, and then I have a control signal, and based on the value of the control signal, I will decide which of the input will be selected to go out. Okay, so in this case, for a add immediate instruction, the write register here is your RT. So I want this to be activated, correct? Okay, this to come here. But you must also remember that at the same time, this is also connected, correct? Okay, so what does that mean? Now what does that mean? That means, okay, this is RS and RT. So if I look at it, I got register 22 here and register 21 here. Okay, that means my data from read data 1, I have content of register 22, and from read data 2, I have content of register 21. Correct? So even though I am supposed to write to 21, but because I specify 21 to this pin over here, that means that data will also come out of the read data 2. Correct? So 21 is now specified in two different locations. I'm specifying it as a read register, and at the same time, I'm specifying it as a write register. Okay, because it's all hardwired. So you must remember everything is, a lot of things are hardwired. Okay, that means it will just propagate through and it will do the selection for you. It is through all our control signal that you see that help us to decide at which point which data I want and which data should go to the next stage. Okay, so a lot of things will flow in parallel. Okay, so as you can see right now, my RT, even though it's a write register, I've also hardwired it to the read register port, correct? Which means that register 21 will be available here, and at the same time, I'm saying that I also want to write to it. Okay, so the control signals here and along the way in the other subsections of your processor will decide what to use, what not to use. Okay, so even though the data is there, it doesn't matter, correct? Because we need to still make a decision whether I want to use this data or I want to ignore this data. Okay, so multiplexer we saw yesterday. So now that I have selected the correct register. So I know that this is my register, which is 22 that I want to read, and this will come out here. And this is what I want. Alright, I want this to come out here, which is 21. And that is based on my register destination selection here. So in this register destination selection, I will know that I want to write to register 21. And at the same time, I will also do a sign extension of my lower 16-bit and present a 32-bit value here. Okay? And why I have to have this multiplexer is because the next stage is to do what? Is to do a add operation. Okay? But in this case, the second data that I supply to my ALU is the immediate value, correct? Okay? So I must set my ALU source to the correct value to say that I want this data that is coming out from the last 16-bit to be selected to go to my ALU. Okay? So at the same time, like we saw just now, 21, register 21 is here, alright? And data of register 21 is there, but we're not going to use it, so it doesn't matter. Correct? So the ALU source multiplexer helps us to make the decision that even though register 21 data is there, we are not going to use it, we are going to use the immediate value. Okay, same thing over here. So if you look at it, the lower 16 bits is immediate value. But at the same time, bit 15 to 11 is still supplied here. Correct? Why? Because if this was an R-type instruction, then I would have used it. Correct? But since it is not an R-type instruction, even though I map 15 to 11 to this pin, I'm not going to use it. Correct? Because that particular multiplexer will be using the register destination pin to tell me that I do not want to look at that. I want to look at the upper bits. Okay, so all the bits, okay, are going to many places in parallel. So it's the multiplexers that help us to decide, okay, at which point which data is going to flow out and flow to the next stage. In a load word instruction, what we saw is the current structure already support your load word. Correct? Why? Because this is your RS, okay, which is 22, and this is 21 and minus 50. Okay, so the current setup already worked because this multiplexer here can select that this is my target register, and this is my RS register, and this is my immediate value. Okay, so the current setup already works as it is. Okay, for branch equal instruction, what must I do? Okay, so for branch equal, I need to do two things, correct? I need to first check whether it is a equal. And second thing, I need to calculate the branch address. Okay, so there are two things that I need to do for a branch is equal instructions. So how do I do this? Okay, so this will be tackled as you saw yesterday in the ALU stage. Okay, so this was the summary of the decode stage that we saw. Now let's look at the ALU stage. So in the ALU stage, basically what we are trying to do is we are trying to complete the arithmetic or logical operation that was specified in the instruction. Okay, so we saw that the ALU, okay, is nothing more than just a block to perform all the operation. And you have two 32-bit input, okay, and you have two output. One is your ALU result. Okay, so this ALU result is the result that is obtained after you perform the operation that is specified, whether it's add or whatever. At the same time, you have another pin called the E0 pin. Okay, and this pin, why is there, is to make our life easier in terms of determining whether a branch should be taken or not. Okay, so this is a single bit. Okay, so this is a single bit, so it's either 1 or 0. Okay, and using this single bit, we can make a decision to branch or not to branch a lot more easily within the hardware, which you will see later. Okay, so that is your ALU unit. Okay, so this bits all no need to worry now. We will look at it more detail in the next chapter when we look at the control block. So this is actually the 4-bit that you specify here to tell the ALU what is it supposed to do. And this we will look in more detail in the next chapter. Now let's look back at this instruction so far and look at how the ALU come in. So if you look at ALU, you know that by default, the first operand will always be your read data 1. Okay, the first operand for your ALU is always your read data 1. Your second operand for your ALU could be either from your register, or it could be your sign extended immediate value. Okay, so in this example, which is a R-type instruction, you know that both of your data are from your register. So what I will have is this, okay, together with this, that will flow inside here, and I get a result. Okay, the ALU control, which you will see later, will basically tell the ALU that I'm supposed to do a add operation. Okay, and I get a result, and later on in the last stage, this will come back here as your write data. So that is the last stage which we will cover today. Now for branch instructions, what I need to do two things. I need to check whether the branch is supposed to be taken, and at the same time I need to compute the branch address. Okay, how do I compute the branch address? If you recall from the previous slide and the tutorial, this number is what? Your number of lines, okay, of code. Okay, so that equates to 3 lines, means you multiply by 4 to know number of bytes, correct? Okay, and to multiply by 4 is left shift by 2. So what we need to do is the lower 16 bits, which is your immediate offset, I sign extend, and then I left shift by 2 to prepare this. Okay, and this will be what? This is the immediate value multiplied by 2 to come here, and what I present at the other side of the adder is your PC plus 4. Correct? And then I have a multiplexer here to decide whether I should be taking the branch or should not be taking the branch. Okay, so based on that decision, this PC source value will be set. Okay, after I decide whether the branch is to be taken or not to be taken. Okay, next we talked about the memory stage. So for load word and store word instruction. Okay, memory stage is basically you are either going to read from memory or write from memory. Okay, and it's the same concept as just now instruction memory. Only thing is, instruction memory you present the address and you only read, whereas in data memory you can read and you can write. Okay, so that is why you have a address together with the write data. Okay, in instruction memory you don't have the write data. Okay, so the concept is the same. I present an address, and in that address, if I'm going to read data, I must trigger the memory read pin. Then I'm going to read the data. If I want to write data, then I must trigger the memory write together with the data that I want to write. Okay, so let's look at the load word instruction. In load word instruction, what do you have? Okay, so in load word instruction, this is your RS, which is your 22 here, and this is my 21, and this is my minus 50. So what will happen? Okay, so your RS will come in here, and that data comes out here. Alright, so the data that comes out here is your RS data, which is your 22 register. And then your register destination will do what? Will select your RT to be the write register here. Correct? Why? Because the data that this is giving me an address, and from the address I'm going to take the data, correct? And the data needs to be written back into this register here. Okay, so the RT will be channeled to be the write register based on your register destination setting. And then what will happen? So this is of course also selected here, as I said just now. So 21 will also come here. Correct? But it's not being used, it will be ignored because your ALU source will select that the value to go to your multiplexer is your 32-bit value, which is your 16-bit extended value. So your ALU source multiplexer selector pin will channel the correct data to the ALU. So what comes out of here is the address, right? The address, which is your base plus the offset. And after that, you must also trigger the memory read pin, because you are reading from the memory. Okay, and what comes out is the data that will eventually be written back here. Okay, so that was your load word instruction. For store word, okay, so in store word, what do we need to do? So in store word, we still have your RS here, and you still have your RT. So this part, which is your RS plus offset, will still remain the same. Correct? RS plus the offset will still remain the same. So this part here, come in here, the offset gets sign extended, okay? Okay, and you get the final address. So that part remains the same. But now I know that the instruction is telling me that the RT is not the destination register to write to. It is actually holding the information that is supposed to be transferred to memory, correct? Okay? And since I know that this 21 is coming here and here at the same time, so what does that mean? 21 is coming here, correct? 21 is coming from the RD2, the read register 2. Now this 21, this multiplexer already selected the sign extended immediate value to go to the ALU, correct? Okay, so I cannot switch the multiplexer in between. So what I can do is I can hardwire this data to my memory. Why I can hardwire it? Because even if there is data here, I still need to trigger this pin, correct? To write to the memory, correct? So even though there is data there, I will not change anything unless the memory write is triggered. And the memory write will only be triggered if I have a store word instruction. Okay, so that is why the hardwiring works. So even though I hardwire the pin, the data will not get written to my memory because it will still need to wait for my memory write signal to be triggered. Okay, so that is your store word instruction. Now let's look at the add instruction. So in the add instruction, what will you do? So in this case, you have your register 9, 10, and your register 8 here. So in your add instruction, this will come here, RS will come here, RT will come here. So what you get here is your register 9 and register 10. Correct? And then what will you do? So this lower 16-bit will also get sign extended. Correct? But I will not use it. Okay, why I will not use it? Because my multiplexer will select the ALU, the RD2 to go through. So this multiplexer here, there is a selector pin that will select the RD2 to go into my ALU. Okay? In this instruction, bit 15 to 11 will be transferred here as my write register. So when I get the ALU result, okay, I will activate the memory and I will also pass it through to the multiplexer. Because this is a hardwire, correct? That means the ALU that compute this final value is now being sent to my memory and also sent to my multiplexer. Okay? So right now, let's say this is value, let's say the value is 3 and value is 2. So I would have, okay, 3 and 5. Okay, so let's say the value 8 here. Okay, so this value 8 will come to this memory and trigger the address bus, correct? Okay, so what will happen? Okay, that means the data in memory 8 is activated. Okay, but since I do not do any memory write or memory read selection, the data is not going to come out. Okay, the data is not going to come out. So even though I present this value to my data memory, okay, I still do not need to worry about it because I did not trigger the memory write or memory read, and at the same time I have another selector here to tell me whether I want the data from the ALU result, which is this, okay, or I want the data from my memory, which is this. Okay, so both will come out. Something will come out of the memory, and at the same time, you have something coming out of the ALU. Okay, but in this case, the memory to register selector will be set accordingly so that I know I want the data from the ALU result, because this instruction has nothing to do with memory. Okay, so the ALU result is the one that will be selected to go out of this multiplexer. Okay, so now let's go to the last stage. So yesterday we actually covered these 4 stages. Now we're looking at the last stage, which is your register write. Okay, so in your register write, what do you see? Register write is the type of instruction where you complete the whole operation, and finally what you want to do is you want to take that final result and you want to write it back to a register. And this is in the beginning stage, correct? Because the register file is now accessed 2 times in your program. Okay, it's 2 times in the program. Why? The first time is to get the data, do the operation, and then now you're going to go back again to update the register value. So how do I connect it? So after this last multiplexer over here, this comes back, okay, all the way to my write data here. Okay, so that is the result of my ALU operation, which is from data register 9 and data register 10. Okay, and once this data comes back here, this write register is already specified over here as my register 8, correct? And my multiplexer here, this selector would have selected the register 8 as the register that I want to do a write back to. And once everything is complete, I have the data. Okay, and then I look at whether the register write is set. So if the register write is set, then I know that I need to update my register, okay, at the end of this instruction. So that is the last stage. So this last stage is only there if it is a instruction that is going to update the register. Okay, if there's no need to update the register, then I don't have this stage. Okay, almost all instructions will have this last stage, correct? Because effectively you're doing an operation and you're going to write back to a register. Okay, only the instruction like store word, then you're taking data and writing to memory. Then there is no write back stage. Other than that, almost all instructions that you see, you will have some form of write back. Okay, so before we look at the next chapter, just to let you think, okay? So if I look at this, register 8, if I give my instruction as register 8, 9 and register 8, then what will happen? Okay, that means I am going to specify register 9 over here. Okay, I'm going to specify register 8 over here, correct? And then I am going to specify register 8 again over here, correct? Okay, so 9 and 8 come out here, and I'm also going to write back to 8. So is this possible? Can I read and write at the same time? Because now I'm telling the processor that I want to read from register 8, okay, and register 9, and the answer go back to register 8. So now let's look at the register file. So in register file, I select 8, 9, and 8, and also I select 8 at the same time. Okay? Can I, if I read and write at the same time, what will happen? Rightfully, you should not do that, correct? But yet, this is a valid instruction as well, correct? In our processor, we've been continuously doing this. So how does it work then? How is it I'm able to read and write at the same time? Okay, so this again comes back to the clock. Okay, so as we have seen, your system is clocked continuously by a system clock. So if I say I'm positive edge triggered, okay, then this is where I will start to execute the instruction, correct? And in all likelihood, this stage here will be completed within the first half. okay, within the first half of the cycle. Okay, that means I can complete my write back in the second half of the cycle. Okay, so what the processor will do inherently is this register write will only be activated, okay, in the second half of my cycle. Okay, so in the first half of the cycle, I can read the data. In the second half of the cycle, I can write the data. Okay, that is why it is still possible to do this within one instruction. Okay, because it breaks up your clock into positive cycle and negative cycle. Okay, so again, you don't need to worry about this. This is more for the hardware design, right? To make sure that I can complete this one instruction in one cycle. Okay, so this basically covers up the whole sort of processor, except what we have not covered shift instruction and jump instruction. Okay, where is shift and jump? Okay, so shift is actually here, correct? Okay, if you look at your R-type instruction, your shift amount is specified as your bit 10 to bit 6. Okay, so if I want to implement a shift, I now need to look at this shift amount bits and then pass it through a shifting block. Correct? That will give me the final result. That is one thing we never look. And the last one we never look is your jump instruction. Jump instruction, basically, you just look at the full 26 bits, correct? After your opcode. So what I need to do? I need to do something, correct? I need to take the 26 bits and then do what? I need to do two things, correct? I need to shift left by 2, correct? And then what do I need to do? I need to add with what? With my PC, not PC, the upper 4 bits of your PC, alright? Upper 4 bit of your PC, then I will get the full 32-bit address to jump to, correct? Then I need to get the full 32-bit address to jump to, and then I need to decide what to do next. Okay, so that basically sums up the full complete data part. Okay, so this data part is important. Okay, that's why I sort of went through again from yesterday, because I want you to understand. Okay, because it's important. Important means what? Sure, come out one. Okay, confirm plus chop plus guarantee one. Okay, every exam sure we ask one. Why we ask this question? Because it's very easy to ask. Okay, why? Because the solution is usually draw one line, that 20 marks, wow, happy. You don't know how to draw, that's it, gone. Okay, so you must know how to, so you can look at past paper, it's always the same one. We will say that we modify the processor, blah, 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 to do something new. And then what must you do? You must figure out where to draw the line to where, and do what. Okay, so most of the time is modifying the multiplexer, adding some new hardware, okay, and then maybe you say, okay, for this new instruction, I must step from this particular register, or I must step from here, okay? So that's the usual pattern. So as long as you understand how the instruction is being decoded and sent through the processor, you will know where I can tap this signal from. Okay, so you must know that if I want the RS, where do I draw the line? If I want to create a new branch address, where do I draw the line? Okay, if I want to implement a new arithmetic operation or new logical operation, where should I go and do it? Alright, so you must understand how this whole thing works. Okay, in the next week's lecture, we are going to look into the detailed design of all these control pins. Okay, how do I come up with all these control pins? Because these are the pins that actually make a big difference, correct? Because your 32-bit that come out go to a lot of places at the same time. Okay, these control signals play a very important role in telling us which data go where. Okay, so that is next week's lecture. Okay, so in next week's lecture, we will look at your control design block. Okay, and how these signals are generated. Okay, so that's the end for today. Okay, any question you can ask me. If not, I'll see you all next week.
The data
data memory is RAM lah.
It's RAM. Then the register file is also the CPU.
Inside the processor. Instruction memory and data memory are outside the processor.
So after the ALU, right, let's say just now you say register 7 and register 8, for example. After you add out, right, why does it go into data memory?
Because that is hardwired already.
Hardwired.
That means there's already a wire that takes the ALU result and sends to the address. Because we do not know whether it's going to be a add subtract instruction or is it a word store word instruction, right? So I sort of do both together, and then later on the multiplexer and the MEMS to register pin will tell me which one I need to look at.
But which address you store inside the data memory, do you know, or it's just a random? Because you say it's
For
hardwired.
for which instruction? The end
So
instruction.
for after ALU, right, you say it's hardwired into
Yeah, so
the data
if
memory.
it was a load word instruction or store word instruction, then the address is basically what you compute, correct? If it's an R-type instruction, then there's no memory access. Alright?
Instruction you need to store into the
Register.
register.
So there's nothing to do with memory.
If load word, I need to deal with memory.
Read from memory, correct?
Read from memory. Yeah.
So if the R-type, then there's nothing to do with memory.
Oh, so the hardwire is to read from the memory.
In the case where you need to read from the memory, then the data will be selected based on the multiplexer. Sorry, who came first?
First tutorial session.
I didn't think it start there. You register to.
Only from it.
Yes.
It only comes from right.
No.
So right, we say just proceed. So after you do like all the computation and stuff, if you write back,
Yes.
then that's it. You trigger the right data.
就是他说直接
So in this diagram, also I looked at a past year paper, is this diagram, it just says piece, program counter source, right? My most actual real diagrams I've seen is like jump and branch, there's instead two. So which one do we have to know?
Yeah, we haven't completed this yet.
No, but like in the past year paper, I also see piece, program counter source instead of jump branch. So which one is the one that we'll actually be learning most of the time?
PC source is a general name. In next week lecture, then we will actually
Or split it into two?
split it into.
Okay, I see.
I want to ask, what does this shift to shift like?
Because you're 26, so this is 26 bit, correct?
Yeah.
26 bit shift left, you get a 28 bit because your last two bit will always be 0, correct? So that's why you shift left by 2. So your last
Shift to this
28 bits. 26 bits, this one we got 26 bits. Shift left by 2, you get 28. Then you add the upper 4 bit, then become 32.
So the upper for me I can directly get.
Take from 4 bit.
So it's 26.
Yeah, you look at it next week.
Also for AOU control. So which one will be set up?
That one is also control block. So all those control signal is next week.
Now, one last question is that
No, we're not going to cover that.
we never complete. Mine is quite long.
Okay. Just want to clarify, with the mem, right? So when you exercise the mem, right, it just reads the right data, right?
Memwrite is to update the data memory.
Update the data memory, so it doesn't use the address, but it
We use
uses
the address because you update some memory location, correct?
Okay.
So the address tells you the memory location.
Okay.
Then the data tells you the data, alright? Then the memwrite is the pin to trigger the memory write.
Okay. And then if you trigger, we set mem read
Then you just look at the address,
address,
and then based on that data in the address, that will come out.
then it will use that data.
That will come out of the memory. Yes.
Okay. And with the ALU control, that is equal is 0. That is again, what is that again?
That is to make our life easier for the branch check.
Branch check.
Yes.
Oh.
We will look,
but the
next week
equal
we'll come back to that again.
Okay, but then in this one, it means we will not be using like the greater than or less than.
No.
There will be nothing about this one.
We are not, we will sort of look at that next week under the control block.
The jump 26, then you shift left for 2 to make it 28, then you take the 4 bits from PC. But why are you taking from PC? Shouldn't you make it all 0 to add to the PC? Because you are...
Yeah, so the upper 4 bit, we assume the upper 4 bit will remain the same. So the jump address you calculate is based on 256 megabyte bound rate, correct?
Okay.
So the 26, so we say the last 2 bits will be 0.
Yeah, because that's a word, right?
Yes, so that's why we shift left to make it 28.
Yeah.
Alright, and then the upper 4 bit we fed from the PC value, so we get the final address that we want to jump to. Because you need a 32 bit address to jump to.
So you're assuming your PC is first 4 bits is different,
Yes.
but the last
No.
28 bits is all 0?
No, we assume the upper 4 bits will be the same. And then the other bits can change.
Okay.
That's why we take the 4 bits.
Okay.
Okay, actually I want to ask the final question regarding question 1. So they tell us to convert this whole part to MIPS code. Yeah, then okay, the assigning part I know because it's rather simple, but the problem comes when we start to assign like string low when we play with the index and stuff. Like I don't know when we taking address, when we taking data.
It's up to you. I mean, when you're taking it.
Yeah, like which part of my code will take. Like, I don't know when, because in normal C programming, I know I taking.
So basically,
data.
if you look at this, any instruction like this, alright, that means you are accessing a memory, alright? And this means you are accessing data.
Huh? Like accessing memory.
Because this is in your data memory, right?
So if load word like that, right? So I'm taking the data inside here.
T1 plus 0. So T1 must already hold
The address.
the address of this variable, the base address of this variable. Then of course, after you bring it in, then subsequently you can just,
So 0 offset of this address, I take the data, I put inside T2.
yes, correct.
Okay, so when I'm taking integer, right, do I use load word or load
No byte,
byte?
no byte.
How come cannot use load byte?
Because if you take one word, then you take 4 characters.
Yeah, but I thought integer is 32
I know
bits.
integer is for byte.
Yeah, correct, but this character one,
Oh no, he asking integer is the one.
integer is lower, right? Integer is lower. In this case, it must use low bytes. Because it's a character like that.
But then I guess relative, like, I'm not sure if it's like we have 5 characters, like hello, and if we think about this, because 4 bytes have 32 bits, like that's 1 line.
Yeah?
And then how does it access like the 5th character?
So
Does that just go into a new address, like a new?
you will go to another new memory location. I think you will do that in this week's lab. You will see the memory. Have you done this week's lab?
No, I haven't.
You will see that. So you will see how hello will actually be stored in memory. So you will see that hello occupy, HELL will occupy one word,
Yeah.
and then it will come another new word.
Okay, so it'll just be right below, like.
Yeah, you only occupy one character in the middle.
Okay.
So for that, right, for example, you for add multiplexer on the so at first you tell yourself first, right, what is the word means. So afterward, right, after all the AI you right, then the multiplexer will tell us whether we need to register or not. Then you only need the key and after that you only tell us where is the register. Then for the this one
Remember, the register can have any value, and that value will come back here. But since the register right is not triggered, it doesn't matter. If it is a lock word, it will forward enough, right? The register right is not triggered. So even if something comes back here, nothing will.
pseudo, so it's not like a full MIPS thing. Can I write that test or exam?
We will usually tell what is allowed lah. So we'll give you the instruction set in the exam, and we will tell you whether pseudo instructions are allowed or not.
Oh, okay.
So if it's allowed way, then you can use. If it's not allowed, then you must use the instruction.
Okay. So to interpret this is if T0 is not equal to S3, then you will jump to 0. If not, you will just continue.
But in this case, you will also check.
Yeah, that's set less than because it's low less than high first. Then if it's low, then you will go to
Because I want to ask, right? So what if I just use instead of this?
yeah. If it's lower, it will become 1. Else it will become 0. So I'll check whether it is equal to match.
T1 is 1.
But then my friend say you must check whether each one of them equal to 0. I don't know why. Because if one is 1,
Because
one is 0.
this is an AND operation.
Yeah.
So I want this condition and this condition to be satisfied.
Yeah, but if either one is not satisfied, I won't go in with this.
No, yes, correct. So either one not satisfied. So it depends on how you check lah.
Yeah.
So you can either check for the.
So if I check if this is 0 or this is 0, either one of them, then I can choose 0. If match is equal to 0, or low less than high is not true. So,
Then it's right.
yeah, so I'm doing this because I'm checking if low is less than high, or if match is equal to 0. So for example, low less than high it's true, then match is not true. So this is 1, this is 0, it will straight away go to because my friend say must use bunch equal.
This is set if S0 less than S1. So S0 less than S1, you do not want it to be, you want it to be set, right?
Yeah.
So it will be 1, so it's not equal to S3. Okay, so it's fine, yeah. Yes.
So I don't need to check individually equal to 0.
I mean, it's just like coding, there's no
Okay.
way, like, as long as the logic is implemented, whether you use, you check in one way, you check equal, check the not equal, it's up to you.
Okay.
So for example, if let's say it's at I, so at I then there will be R register 2, right?
RS and RP lah.
Yeah. So for example, you are saying that here, right, you come here, then they will, the multiplexer will decide whether to go to register 2 right register.
No, you still go to register 2, right? It's hardwired.
But it's hardwired. Then,
What comes here is whether it's RP or the RB base.
so if let's say at I then register 8, register 7, and XP. So 8, 7, register 8 will come here, right?
Yes.
Then register 7 is register 8 is supposed to be removed.
So you come here, and you specify here, right?
Yeah.
And that will come here.
So they won't come here.
It will come there also.
They will come. So the
It will come in two places.
but this will not be yours.
You come out here also and do this. You come here, but this ALU source will not use this data, it will use this data,
Why not just put a multiplexer in the middle, then they will decide where to go. Like don't even go to the R2.
Because you don't need to, the problem is the differentiation between
This one is
because
this one will be the immediate constant. Alright, then this one will be the stop. So the stop is supposed to come here. Then the immediate constant will
because basically you see for R type, this one is the extension. Alright? For I type, this one is the extension. So that is the difference. That's why
also they will go both ways, but in the end it will only be one. But this one is like it's not, but it's not used. It's not like then the immediate will be if it's a I immediate will go with the
then immediate will come here.
so we'll straight away extend 0, 0, 0
Yeah,
in front.
straight away.
Then it will straight away
Come here.
multiplexer here is do decide
Which one to select for the ALU operation? So is it the register data or is it the shift data?
okay, so then they will come here and calculate, and then after that, then for this part is
CC. Give me a minute. So what's your question?
It's actually about last week's actually. Yeah, kind of confused about the byte addressing.
Okay.
So, I mean, we have this diagram, right? So, we have the address bus, and then the address bus have a certain width.
Alright.
Right? So, from that, we can say that if you have a 1-bit address bus, you have 2 values use for your address. That's correct, right? So that one is okay. But for the data bus, you mentioned that the size of the register is 4 bytes, and the data bus will probably be 4 bytes as well. Like, is that I mean, it can be smaller as well, right? So then you'll just not be able to.
Then you may not be able to complete your access in one cycle.
Okay.
That's all.
Right. Then, so if your data bus is 4 bytes, it doesn't mean that your each like range of your address is also 4 bytes, because in our case we are using byte addressing, although the register is 4 bytes. So as in, I'm just saying, like, it doesn't have to be the case that your memory is sectioned into 32 bits as well.
I mean,
Your register is
for
32
MIPS,
bits.
since we deal with 32 bits, we say that every time we do any address, the instruction is 32 bits. But data also, we treat it as it's byte addressable, alright? But then we treat it as words.
Yeah, but it's actually byte addressable. Like, you can still load a byte.
Yeah, correct.
But let's say that you can load a byte because byte is small. Can you load a bit also?
No.
So if it was like 32-bit addresses, then you cannot load a byte.
Okay, I hear you get mixing up. The 32-bit address specify one location.
Yes.
In one location, what is the data I have?
Okay.
So if I say it's byte addressable, that means in one address I have 1 byte.
Yes, that's it.
Okay, so that is why we every time increment the address by 4.
Yeah.
But if I use load byte or store byte instruction, then I can also read and write in bytes.
Yeah, that's okay.
Alright.
But
So that is the lowest denomination you can use.
so like what I'm saying now is, if instead of byte addressing, they're using 32-bit addressing. So you have 32-bit addresses, and each address has 32 bits instead of having a byte. So in that
No, in
case,
each address,
Yeah.
there is. So you're saying it's a word address.
yeah,
That means in each memory location is one word.
32, yeah, one word.
Okay.
So then I can't access a byte.
You probably need to then read that whole.
Okay.
Then you need to do your own reading in the code lah.
Okay.
What is it?
So for example, you mentioned like numbers like branch equal, then they will shift 2 lines. So 2 lines they will times 4 bits because shift 2 bits. Then you say here we decide the branch taken or branch not taken. What do you mean by branch taken?
Because the instruction got BEQ or something, right? So the BEQ, you must know that whether it's equal or not, right? So even though I calculate the address, I still don't know whether I know whether
However, if branch equal to 0, so if equal to 0 is branch taken.
so let's say branch equal. So for example, I still need to read register 9, read from register 0, then I need to do a check. So only in the ALU stage, when I do the check, then I know whether the branch is yes. Then I need to decide, right? So that is where the multiplexer comes in.
So if branch is equal means they are equal. In this case, then they will jump. So if they are not equal, then branch is not taken, which they will not. They will just continue.
Correct.
Also, branch taken means equal. Branch is not taken means.
If you walk the top.
Ask anybody, yeah, I need help with this. Dumb fuck.
You good at this shit?
I'm okay with this shit.